Our final chapter this semester is a brief introduction to elliptic curves. This is a very deep area of number theory with lots of applications. We're only going to spend a few days on it, but I want to get you to the point where I can show you how elliptic curves are used for factoring whole numbers. So the overview is we'll start by defining an elliptic curve, or rather reminding you what we did last time. An elliptic curve is just a non-singular cubic curve. And one way of describing what non-singular is to define the discriminant of a cubic polynomial. So we'll remind you what that means. There's two types of cubic polynomials, the one component and two component types. When we view them as curves over the real numbers, we need to talk about the point at infinity and then how to add points on the elliptic curve in order to turn it into an abelian group. And then I'll give you an example in this section of a cyclic group of points on an elliptic curve. Okay, so let C of f be a curve defined over the real numbers, defined by this equation. Y squared is p of x, where p of x is the polynomial x cubed plus ax squared plus bx plus c. That's going to be our canonical form for an elliptic curve. So a, b, and c here are real numbers, and we define f to be the polynomial in x and y defined by y squared minus p of x. So if this curve CF is non-singular, then it's called an elliptic curve. More generally, an elliptic curve is any non-singular cubic polynomial. The form 1 is just a particular type of cubic polynomial, but it turns out that any non-singular cubic polynomial can be transformed into this canonical shape 1 by what's called a birational transformation. So it's a transformation where the two coordinate functions are rational functions in x and y. We're not going to get into that here. We'll just assume that all of our elliptic curves have the form given in equation 1. So what does it mean to be non-singular when it's given in this form? So at any singularity, the two partial derivatives have to vanish. So we have three equations then. First, the point must satisfy the equation. So we have y squared is p of x. Second, when you take the partial derivative with respect to y, you just get 2y, and we have to set that equal to 0. And third, when you take partial x, we get 3x squared plus 2ax plus b equals 0. But the point here is that when we say y is 0, that means you've set p of x equal to 0. And so in order to be at a point of singularity, you need p of x and p prime of x to be 0, meaning x is a double zero of the polynomial p of x. So that leads us into the discriminant. So recall, if p of x has a factorization like this over the complex numbers, where r1 and r2 and r3 are the complex zeros, the discriminant is defined as the product of the differences of the roots squared. So r1 minus r2 squared times r1 minus r3 squared times r2 minus r3 squared. And so immediately you see that the discriminant is 0 if and only if one of the ri's equals an rj. In other words, you have a multiple root for some I and j. And there's a formula for the discriminant that you derive in your algebra classes. So if the cubic polynomial is given without an x squared coefficient, the discriminant is minus 4a cubed minus 27b squared. So this is the analogy of the famous b squared minus 4ac discriminant you see for quadratic polynomials. It's a little more complicated if you have the x squared coefficient as well. So generally what you do is if you start with a cubic polynomial with all of the coefficients, you make a substitution. You replace x with x minus a over 3, and by doing that you'll eliminate the x squared term, and then you can calculate the discriminant using this formula. And it's quite obvious that the discriminant is invariant when you translate the variables, because you're just translating each of the zeros, and so when you subtract the zeros you're getting exactly the same value. So we've seen then there are three different equivalent conditions for the cubic polynomial y squared equal p of x to be a non-singular curve, to be an elliptic curve. So the curve is non-singular and therefore is an elliptic curve. The polynomial p of x has distinct roots, or we can say the discriminant of p of x is non-zero. Over the real numbers, we get two types of curves when you're actually sketching the graphs. We can have two components. So if the discriminant is positive, that means the polynomial p of x has three distinct real roots. I'll let you think about that. And so the curve will have two components to it. I'll draw a picture in the next slide. And if the discriminant is negative, that means the cubic polynomial has one real zero and two complex zeros. And so you end up with a single component when you sketch the curve. Okay, let's look at a couple examples. Take the curve y squared equals x cubed minus x. So this is x times x squared minus 1. So y is 0 when x is 0 and plus or minus 1. And let's go ahead and calculate y prime. So 2y prime is 3x squared minus 1. So y prime is 3x squared minus 1 over 2y. And so it's infinite. You'll have vertical tangents when y is 0. And you'll have horizontal tangents when x is plus or minus 1 over root 3. Like that. And so if I'm sketching the curve, we've got zeros at right here, 1, and negative 1. And then at these points, that's about negative 0.5 something. You're going to have a horizontal tangent, maybe like this. And notice that the curve is symmetric. It's going to be y is plus or minus the square root of x cubed minus x. So it's symmetric about the x-axis. And when x is bigger than 1, we would have a perfectly well-defined positive quantity on the right-hand side. And so the curve will do something like this. Okay, so what am I doing to think that out? We have a vertical tangent when y is 0, so it's a vertical tangent here. And when x gets large, y is roughly x to the 3/2 power. And then you have the symmetry. Between 0 and 1, the right-hand side is a negative quantity. And so there is no solution. And then to the left of negative 1, we also have a negative quantity on the right-hand side, and so there's no solution. And then between 0 and negative 1, the curve will have its horizontal tangent, it'll have a vertical tangent, and it'll be nice and symmetric. And so we have these two components here. So that's a typical two-component elliptic curve over the reals. And then for the other type, when you factor x cubed plus 1, you just have a single real zero and two complex zeros. The two zeros of the quadratic are complex. And again, the derivative x squared over y. So it is 0 when x is 0, and it's vertical tangent when y is 0, and y is 0 when x is -1. Okay, so at -1, we're going to have a vertical tangent. There's +1. So we've got a point here. When x is 0, y is plus or minus 1. Again, nice and symmetric. And we also said when x is 0, you're going to have a horizontal tangent. So it's vertical tangent here, flattens out, and then when x gets large, y again is roughly x to the 3/2 for large x. So it's going to just come up, and what did we say when x is 1? Well, it's not even anything special. Kind of goes up like that. Nice and symmetric about the x-axis. And we just get a single component. Okay, now why did we want this curve to be non-singular? That was so that we would have a unique, well-defined tangent line at every point. And we saw that in the previous section. So what was the equation of the tangent line? You look at the gradient of f evaluated at your point P, dotted with x minus x naught, y minus y naught equals 0. The gradient is perpendicular to the curve, and this is your direction vector along the line. Moreover, when we draw a tangent line to the curve, it will intersect the curve at a unique third point, counting intersection with multiplicity, provided that it's not a vertical line. And if the curve happens to be defined over the rationals, and you're at a rational point, then that third point of intersection is a rational point. So definition, if the tangent line to the curve has intersection multiplicity 3 at the point of tangency, we call this point an inflection point of the curve. So let's look at an example there. Let's take the curve y squared equals x cubed plus 1, the first example we looked at. The second example, that's the single component curve like this. And we can see that it clearly passes through these integer points, 0 plus or minus 1, -1, 0, and 2 plus or minus 3. These 2 points are nice points to draw on that curve. I claim that points B and E are inflection points. So let's look at the tangent line at B. So we have to find the slope at the point B, and well, we already did that. 2y prime is 3x squared, so y prime is 3/2 x squared over y. And so the slope at B is 0. And the tangent line, that's not the tangent line. Scribble, 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 scribble. Tangent line would just be y equals 1. So intersect tangent line and curve. And what happens? So here's y equaling 1. And you can see in the picture, it looks like it's just hitting the curve at B. but you can do it algebraically. Y equals 1, intersect that with a curve, you get 1 equals x cubed plus 1. X cubed is 0, and we can see a triple 0 when x equals 0. Okay, so that's a typical inflection point. And then the point E, it works exactly the same way. Now, this curve has another interesting feature. Look at the tangent line at C, for instance. So here m is 3/2 x squared over y, so that'll be 2. Okay, so if I'm at the point E right here, and we draw a little slope triangle like that, so the change in x is 2, and the rise is 4. So exactly, you can see that the tangent line at C is passing through the point E. So it passes through E. Well, that's neat. And what if we look at the line segment joining A and B? So that's of slope 1, obviously. And if we just continue going up a slope 1, and so move over 2 units, move up 2 units, we'll be exactly at the point C. So the line joining A and B passes through the point C as well. And so what we discover is the following. Note, the tangent line at 2, 3 intersects the curve at 0, -1. The tangent line at 2, -3 intersects the curve at 0, 1. The line joining -1 and 0, 1 meets the curve at 2, -3, etc., etc. You end up with a closed system of points when you try to use chords and tangents to construct new points of intersection. And this suggests that we are forming some type of group. So a group is a closed system under some binary operation. And so that's what we're doing in this picture here. We're taking 2 points, draw a line to find a third point, or connect B and E, try to find a third point there. Well, that's going to give us some problems. Let me come back to that one. But D and E hit the point A, the tangent line at D hits at B, and so on. So the two problems I was just mentioning, if you have a vertical line meeting the curve at 2 points, we don't have a third point of intersection with the curve. And then finally, if we're actually going to form some group here, we need an identity element for the group. So to solve these two problems, what we do is introduce a new point called the point at infinity. So we introduce a new point at infinity, denoted P infinity, and just think about that point as sitting way up here. It's just some point at infinity. And we say that every vertical line passes through this point. So P infinity is going to serve as the identity element for the group that we're going to construct. And by introducing this point, then every line that hits the curve at 2 points will meet the curve at a third point. So if we have a vertical line passing through, say, B and E, we're going to say that line passes through P infinity. Or a vertical line passing through C and D, we're going to say that also goes through the point P infinity. And the tangent line at A hits the curve twice at A and passes through this magical point P infinity. Now, we'll come back next time to really make rigorous what is this point at infinity. How can all these different lines be passing through the same point? But let's just take that as a given here for now and introduce a notation we're going to be using. So if I give you 2 points P and Q on the curve, I'll let PQ denote the third point of intersection of the line joining P and Q with the curve CF. So if my elliptic curve is a single component curve like this, and we have a couple points P and Q, draw the line here, and we'll call this point PQ. Just a matter of notation. PP would denote the third point of intersection for the tangent line at P with the curve. And if P is an inflection point, so the tangent line hits the curve 3 times at that one point, PP would equal P. We'll let P infinity denote the intersection of a vertical line through P with the curve. So here I've got a vertical line passing through P, and then P infinity would be this point right here. So in other words, P infinity is just the reflection of P through the x-axis because of the symmetric nature of our canonical curve. All right, let's look at this example again, y squared equals x cubed plus 1, and just show you how this notation works. So the point C is the same as AB. Okay, so let's go ahead and you can work these out. Find AB, find BC, let's find CD, find BE, or BB. All right, just try to look at a few examples like this, or how about CC? Okay, so AB we said was the point C. BC intersect with the curve and you get A. CD, that's a vertical line. So where does it hit the curve at a third point? That would be at the point at infinity. BE, that's also a vertical line, so that would have to go through P infinity for its third point. BB, that's the intersection of the tangent line at B, but this is an inflection point, so it only hits at B. CC, that's the tangent line at C, which will hit the curve at E. So that's the idea. Next, we'll define an addition law on the elliptic curve. So if I give you 2 points P and Q on the curve, we'll say that P plus Q is the point PQ times P infinity. Well, not times, it's just the line segment. So what do? PQ itself is the third point of intersection of the line segment joining P and Q, and then you want to reflect that third point through the x-axis. So it's the reflection of PQ through the x-axis. So now let's look at this collection of 6 points that we've been dealing with on this curve. We've got P infinity, we've got the points A, B, C, D, and E, all nice integer points, and let's call G that collection of points, and we're going to have an addition law defined up here. And I claim that we have a group. In other words, that this addition law is an associative addition law, that there is an identity element for the group, and that there are additive inverses. So first, let's just do a couple examples. Let's find A plus B. So by definition, that means AB, P infinity. So AB is C, the third point of intersection. And then CP infinity means reflect the point C through the x-axis to get D. So A plus B is D. How about B plus D? What's that? So we go BD. Okay, now what's BD? Well, the line joining B and D is tangent to the curve at D, so the third point of intersection is D itself. And then I look at dP infinity, so that means reflect D through the x-axis, and we get C. All right, so that's how we add points on this curve. I claim that P infinity is an identity element with respect to this operation. So let's see what happens. If you take P infinity times, not times, but P infinity plus a given point on this curve. Let's just do a couple examples. So what does that mean? P infinity plus B. So by definition, that's what P infinity plus B means. P infinity B is the reflection of B through the x-axis. So that would be E. Aha! EP infinity means the reflection of E through the x-axis, and that's back to B. And so there was no need for me to be working with the point B. I could have been working with any of the points B, E, C, or D in this one demonstration here. And what we're saying is that when you add P infinity to any one of those points, you're just reflecting that point twice through the x-axis, and so you're right back to where you started. Now it's a little different if we're at a point like A. Let's see what's going on there. If I add P infinity plus A, okay, so what does this mean? Reflect A through the x-axis. Well, that's just A. And so again, we're just reflecting A twice through the x-axis, and it never moves the whole time. It just stays at A. And then finally, P infinity plus P infinity. This, by definition, is just going to be P infinity. So we're going to just make a formal definition here that P infinity is an inflection point. So P infinity is P infinity. So this will be a formal definition for now. And then in the next section, we'll make rigorous this point at infinity. P infinity equals P infinity. And thus we have an identity element with respect to our binary operation. Now I claim that this group G with these 6 points is in fact a cyclic group. So let's show how the point C generates this group. So first I'll take C and add it to itself. So that's what 2C means. C plus C means draw the tangent line at C. Okay, the tangent line at C passes through E, and then reflect E through the x-axis to get B. 3 times C means start with B, which is 2C, and add C to it, so B plus C. B plus C means draw the segment joining B and C. Third point is A, reflect A, and we're at the point A. 4C is 3C plus C, which is A plus C. A plus C, we have B, reflect that, we get E. 5C, you'll get D, and then 6C. You're finally back to where you started. And thus, the order of the element C in this group that we're forming is 6, and so we've got a cyclic group generated by the point C. So a cyclic group of order 6 generated by C. All right, so this is just kind of introducing you loosely to this idea of a abelian group structure on an elliptic curve. So we'll look at that in more detail in a couple sections down the road. But in the next section, I want to make rigorous this point at infinity.